Thanks to the organizers for having me here. I want to talk to you about the quantum chemistry side. So I am at Saarland University now, which is here at the border to France. I'm showing this because everybody asked me where Saarbrücken is. So I was in Mainz before, and now I'm here, very close to France. And I'm in theoretical chemistry, so I'm not an astronomer. But I actually had first contact with this community in 2018, and I keep coming back, and you might wonder why. And the reason is that in my group, we're doing a development of finite field methods, so methods that you can use to put molecule in a strong magnetic field of essentially, in principle, any strength. And that is useful here in the context because we can use this to predict white dwarf spectra, or at least this is what we want to be doing. And this is why I was coming here, to show that we can actually do this and what we can do, and to interact and see whether you have strange spectra that you cannot assign, and maybe we can see whether it's something in a strong magnetic field. So if you think about an excitation, say a S to P transition in a magnetic field, like the most simple picture would be this kind of splitting, and what you would be thinking what happens then is that you just have this like simple Zeeman picture with the linear splitting, with one component like being independent of the field and the other two going linearly. And I guess you all know that this can happen, and you have this kind of splitting for spectra where the magnetic field is not that terribly strong. But of course, it can also be much more complicated if the field is stronger. And these are these nice spaghetti plots from this here from 2014 for hydrogen. So you can see this clearly becomes eventually very nonlinear and very complicated. And these kind of B lambda curves can be used for the assignment of spectra. And for hydrogen, most of such spectra, so you can, you then read off essentially the magnetic field, and most of such spectra have been assigned in the 70s and the 80s for hydrogen. And then there was not much going on for helium because there were no predictions until in the late 90s, Becken and Schmelcher did these kind of B lambda curves for helium, which is of course more complicated. And they did that using full configuration interaction calculations on helium. And you can already see that this spaghetti is even worse, right? And then if you go to the literature, then you can see that actually, this is like about 300 to 700 megagauss. There are predictions for something to up to 3 to 4 electrons, depending how you're counting, but there are no predictions for carbon or metals and so forth. And this is, the simple reason is because of computational cost. And this is where new developments are needed, and this is what we have been doing. So in quantum chemistry, just in a nutshell, what we typically do, because we also can do this for molecules, is we set out with a set of analytic basis functions from which we first, through linear combinations, make orbitals. And from those orbitals, we then set up determinants, so many electron functions. And then you can have some sort of combination of those to represent your final many electron wave function. And in full configuration interaction theory, so what Becken and Schmelcher used, you really just have then the Slater determinants and the linear combination over all of those with some coefficients, which you can also write as 1 plus C, an operator working on some reference, where this operator C is like one body excitation, two body excitation, and so forth until n electron excitation. Okay. And there is another way to parameterize the same wave function, is this via coupled cluster theory, where you have an exponential working on such a reference determinant, and then you write it as 1 plus t squared and so forth. And then the t's in here again are such kind of excitation operators like 1 electron, 2 electron, and so forth. But you see it's a different kind of parametrization, But if you do not do any truncation, so you really go up until Tn, then it's just a like more complicated way to write the same thing. So then full CI is like full coupled cluster. It's exactly the same thing, but there are actually major differences when you truncate it. And yeah, why would you truncate it? To save computational cost, of course, because full CI has a factorial scaling, so that's really just horrible here. But then if you have a truncated wave function, so in the T or in the C, you do not go all the way. Say you do CISD, where you have C1 plus C2, or CCSD, T1 plus T2. This scales like order n to the 6th, where n is the size of the system. And then you can truncate later, C1 plus C2 plus C3, and so forth, and that then scales as n to the 8th. So it's not that bad. It's already not, it's not great, but it's, yeah, it's not full CI. So these tend to have the same scaling, but coupled cluster is much better, like in terms of results and yeah, some properties also of the wave function. So in quantum chemistry, there is like no debate that this is the preferred way to go. And coupled cluster is the ground state method. Then the extension to excited states is equation of motion coupled cluster theory, where you then act with an operator R on your coupled cluster wave function to get the excited state. Okay, like this is all I wanted to say about this. And this is like well established and everything. And what we have been doing, what is new, is to apply this kind of coupled cluster and equation coupled cluster of motion coupled cluster methods for a Hamiltonian that actually has the magnetic field. So this would be the Hamiltonian in this case, where H0 is just a simple non-relativistic field-free many-particle Hamiltonian. But then you have terms that are linear and quadratic in the magnetic field, and we don't treat those as a perturbation, but we really put them in. This is the orbital Zeeman term, the spin Zeeman term, and also the diamagnetic term, which is otherwise often skipped. But if the magnetic field increases a lot, then of course this will be a dominating term. So we also take it in. There is a downside. In a general case, working with this Hamiltonian means that the wave function becomes complex, and most quantum chemistry codes cannot deal with that. So you have to, redevelop these kind of methods and make new software implementations. And this is what we have been doing. So we have like this kind of toolbox of methods. You don't need to understand all these acronyms, but it's like various flavors of these coupled cluster and equation of motion coupled cluster levels, methods that we use for this finite field treatment. Yeah? And with this, it's possible to target states from different starting points and at different levels of accuracy. All right. And then I came and wanted to apply this maybe, or see whether this could be useful also here in your field. And I was talking with Mark Hollands from the University of Sheffield, and he had this spectrum, which to you might look like a strange spectrum. To me, it's like, okay. And this was the star in question. So this star is very close to Ursa Major. Like, at least I care about where this is, so I at least. And if you zoom in a lot on Google Earth, then you can see, yeah, it's actually there. It's quite faint. You cannot see it with the naked eye. But if you compare now this spectrum to something more normal, like a non-magnetic white dwarf that has magnesium and sodium, you can see that like here, even though this is shifted like at about 5 angstrom, but maybe this could be the sodium D line. And then here you have this magnesium line, which is quite asymmetric. And you have something similar maybe here, but it's very far away. So it's like 50 angstrom away, so a very large shift. So it was not at all clear what this would really be in the end, but we then started out to do finite field calculations for that to see whether we can see whether this is actually a magnetic white dwarf with metals. And so how did we do that? So we are doing it via a composite scheme. So all of the calculations are field dependent, but we still do a composite scheme to increase the accuracy. It works like this. So we calculate an excitation energy, but because we're doing an error for the one electron basis, this function chi that I had in the beginning, we're adding a correction, and then we also have a correction for these higher order excitations because we have some truncated coupled cluster treatment. Okay, and then from that we have some corrected excitation energy. We can convert that to a wavelength. And then we have essentially, if we do this for several magnetic fields, then we have a B lambda curve, right, for that sort of excitation. And what we then do is to shift this B lambda curve to start exactly where NIST says it should start, because we do not hit it quite exactly at zero field. There is still like an offset, and then we correct for that in this way. So that is then typically 15 to 20 angstrom off, but then shifted so that the shape remains the same. For magnesium we did some more sophisticated things, but I will skip the details here. So if you look at the excitation, it's actually the total energies in this. So the total energies against the magnetic field, so here's about 470 megagauss. Then for this magnesium transition, it would be transitions from these three states. They are split into this yellow state above here. And you can also see like these two states, they actually go through an avoided crossing. This is because these orbitals in the magnetic field have the same symmetry, because there's a symmetry lowering. So you can already see the electronic structure is a bit complicated. And avoided crossings occur and so forth. And also like these two are not really parallel, so you will not expect the excitation energy to, like for this transition, to be independent of the magnetic field. And indeed, this is what you see. So in dotted would be the simple Z, these are now the excitation energies. The dotted would be the simple Zeeman picture, and the full lines are what we have actually calculated. And you can see, right, so it is really quite off. It changes quite a bit, and it is not linear. And so, yeah, and the reason why, in particular, this line is so far off from, this is the pi component. Why it's so far off is because it's a transition from the 3p naught to the 4s. And in the magnetic field, so these are these three orbitals in the field 3 case. And in the magnetic field, they look similar, they're a little bit contracted. But the 4s is really acquiring d orbital character and really changes. So the states, they do not behave anymore in the same way. So we can, with that, do B lambda curves. So here they are for magnesium and for sodium. You can see the pi component for magnesium moves quite a bit, while the one for sodium does not. So it's quite stationary. But actually, if you try to calculate that at different levels of accuracy, then between those predictions could be up to 100 angstrom. So it's, really needs high accuracy and some work to get that right. And also we have calculated the oscillator strengths also in a field-dependent way. So this is reflected by the opacity of the lines. So now that we have like these pi components, and if we say, okay, let's assume those were sodium and magnesium, we could then see whether we can see what magnetic field that should be. And if you do it, like this is now the pi component for sodium, if you do this, you could see that that could actually correspond to either about 30 megagauss or 400 megagauss. But if you do the same thing for the magnesium component, then it's actually clear it is actually around 30 megagauss. So even though that's not that immense strong field, even though probably the strongest for metals, it's quite strange, right? So then we can, after assigning the pi components, also look which are the sigma components in this. And again, the dotted lines are the simple Zeeman, and assign some of these peaks in the spectrum. Then Mark went one step further and has come up with a simple toy model where you put like 10,000 points here on a disk and use the offset dipole model with inclination here of 15 degrees, and the offset is, minus 0.15. That represented then the spectrum well, it's not a perfect fit, but it's actually quite nice. So that's really just a toy model, but you can get something quite reasonable out of this. Yeah, with that, sodium and magnesium has been assigned. We went a bit further also and did some more calculations. So we also added some transitions for calcium. These are all of the B lambda curves that we calculated so far. And if we put that in also then in our toy model spectrum, then we get some more peaks. Still, there is quite a bit that is not assigned, but I mean, we have calculated also selected transitions. So there's probably also other elements there, like iron, for example, possibly chromium. But yeah, calculations are quite hard for these systems. And then the last thing that we can actually do is to show you, so like if we keep these parameters fixed from the offset dipole model and just then plot the spectra for different magnetic field strengths, then this is what we get out. And this is a paper that, yeah, we are very close to submitting now. And you can see that, like, for example, the sodium, the sodium line, this will be for quite strong fields, quite stationary, while this magnesium one really shifts. And you can see, like, the spectra become really unrecognizable. Even, yeah, this is just like a selection of transitions. Yeah, the last thing that we want to do and have a bit started on doing is to look at molecules. I mean, we have been looking at molecules in strong fields anyways, but I mean now also for astrophysical predictions. Molecules are quite interesting in magnetic fields because they can do strange bonding, like this perpendicular paramagnetic bonding, which looks like where the orbitals look like a donut. Yeah, we want to do that as well in this context, like looking at, yeah, for example, C2. So to summarize, yeah, I have been coming here hoping that this would be useful, and it looks to me that it has been, which I'm really thrilled about. And I sort of, yeah, so I think it's a nice synergy. We have done some finite field predictions for magnetic white dwarf spectra and have assigned these metals in a strongly magnetized white dwarf, about 30 megagauss. Yeah, what we want to do in the future is also add in relativistic effects, because they're so far missing in the treatment. So they are in sort of implicitly, but not in a field-dependent way. And we want to look at molecules. And yeah, let me say, like, if you have strange spectra or suggestions that what we should be looking at, yeah, let's definitely talk. It would be great if that stuff could be useful here. And with that, I would like to acknowledge my collaborators, in particular Mark, and also people from my group, so Flo, who has started this work, and Simon here, and Petros, who have also done more recent implementations and calculations, and thank you for your attention.
Thank you, Stella. Stefano.
Hi. May I start? Which kind of radiative transfer used to go from the splitting and strength of the transition to the spectral lines, to the shape of the spectral lines?
The spectral line, you mean this toy model? This is just a super, like, there's not really physics in this. This is just like sort of taking 3 Lorentzians for like a split line and then trying to fit it. It would be super nice to put that like in an actual atmospheric model, but I think it's already nice to see that this can be already useful. But of course, to have a model where you have the proper physics in, and to possibly also do some calculations for what that physics actually should be, that would be nice. Yeah.
And can you say anything about the continuum in presence of a so strong magnetic field would be also polarized?
What do you mean?
The continuum, I mean, you are only doing the spectral lines, but if you put a strong magnetic field, I guess that also the continuum will be affected.
Yeah. Yeah, there I'm not an expert. I cannot really. Maybe somebody can say something, but I can only do the predictions, so I don't know. That I don't know.
Thanks. I have a question actually about this. Like, for example, the sodium line on the right, you know, it has that particular shape. Does that come from the fact that the geometry of the dipole? You know, the rightmost line that
This
you have.
one?
Yeah.
That comes from the geometry. So like if you, I unfortunately put it out, but like if you play around a little bit, then you can like make them go into this, into the right shape. Yeah, so it comes from the geometry, yes.
In terms of molecules, I think there's cool white dwarfs with carbon bands.
Yes.
That I think cannot be fitted very well at the moment.
Yeah. So this is something that we want to look at, definitely. Yeah.
More questions? I'll first.
Maybe I'm jumping like 10 steps here, but for instance, for let's say just a white dwarf that has hydrogen, at some level we can trace the magnetic field, the distribution, let's say, in the surface. Do you use a constant magnetic field in all the star, and you think that different magnitudes of magnetic field along the surface will change the results?
Yeah, I mean, this is what is tried to be modeled here, right? So, so in the end, you have to take that into account. So, like here in the toy model, you can, the magnetic field is different in like different places. And so you can take it into account. So what we put in, then, I mean, what then goes in that you then calculate what should the magnetic field be at that particular point. And then you just add in sort of the transition that we have predicted together with the opacity that we have predicted. And this is how you get this then in the end.
Okay, great.
So, and yes, and then, to do it really properly, you would then, I guess, put it in the atmospheric model. So.
Thank you.
No, you probably explained this, but I didn't really get it. I don't understand. So you showed how the magnesium central line shifted quite a lot, while the sodium doesn't.
Yeah.
And it was because of the shape of the orbitals, but I didn't get why don't you have that in the sodium?
Because for sodium, so magnesium is a P to S transition. So from the 3p orbitals to the 4s, which is like a main quantum number in between. While for sodium, it is 3p so it's S to P. So it's 3s to 3p. And you have actually, I mean, those are the ones for magnesium, but they look the same then for sodium. Then you have those two, right? And they are also in the field much more similar. So that, like there's like not very different things that happen to them because like they are the same main quantum number. And then this is why, so the S to P transitions will have much more stationary lines than the P to S transitions.
Thank you.
I see you've done calcium, magnesium, sodium, and just thinking about these metal polluter, what those, how would, the next element comes to mind, how hard would silicon be?
If we could calculate it?
Yeah.
Yeah, silicon would be fine. Is that something that you often see?
It's just that what was to show pollution from calcium, magnesium, they often also have silicon, and it will be the next element, I guess.
So how long would it take to calculate?
Silicon is not that bad. I mean, like that, couple of weeks maybe to have it. I mean, what is really more a challenge is like iron. So that's really tough. But silicon is fine. We can do that.
Any more questions? It's a very silly question, but I'm just curious. Why you don't get the correct value as zero field and you need to correct it?
No, because we're still making mistakes, right? So like we don't have the relativistic effects in, and we do make, so we make corrections for the like higher order excitations, but that's also not perfect. And then a quite significant thing is like the basis sets, because like if we had an infinite basis set, then we would not make an error, but obviously it's not possible. And so there are remaining errors, and they simply NIST, like you cannot beat it. It's very, very accurate. But so this is where the remaining errors come from. So mainly I would say basis set, and then for in particular calcium, so there it would be quite important also relativistic effects.
Basically you get the correct shifts still, but not the absolute values.
Yeah. Right. Or so we hope. But it looks okay.
And going back to the molecules, do you already have some, or you are only asking for which one we would like?
Yeah, please, I can give that back to you. Which would be good to calculate? So I heard that C2 might be useful. And right, so of course C2 is the most horrible molecule in quantum chemistry, but sure. Then CH, I don't know. Like I know that H2 had been predicted, had been seen in white dwarfs, but I don't know how. Yeah. So if you have ideas, right? So please let me know.
Yeah. So for C2, the reason it's interesting is because when you look at cool white dwarfs that have C2, the bands are shifted, but it's a bit complicated because there are many reasons why they can be shifted. One of them is pressure effects. But even when we account for that, there's still another shift, and so we suspect there's this has something to do with magnetic fields. And for H2, well, we only see collision-induced absorption in the infrared, so we don't really have the resolution. You know, we cannot resolve where the bands are exactly. So yeah, sorry, but C2 is really what we need.
Yeah, I had hoped H2 would be useful because that's much easier.
Okay, if there are no more questions. Oh,
I
okay.
have do you think that the hydrogen and the helium can be improved, or do you think the computations are?
No, I think they are very good. I mean, no, I don't think so. I think they are very good. They have really done an excellent job, and they have, like, at least to my knowledge, made predictions such that the error is like within 10 angstrom. So I think, yeah.
Thank you.
Thank you, Stella.